Hey, everybody. So we are still talking about limits, but we're going to look at a different kind of limit today. We're going to start by taking a look at this function. So I've got a rational function here, k of x equal to 1 over quantity x plus 1 times the quantity x minus 2 squared. Okay, so it gives us this this fun graph, right? It's kind of a surprising graph, does a lot of different things. There's a lot to examine in this, but we're going to look in particular at what happens at a couple of places where this function, or near a couple of places where this function isn't defined, right? First, notice that our function is not defined at x equals -1 and x equals 2, right? You've probably heard the term asymptote before. We've got a couple of asymptotes for this function. Right? They're not defined. The function is not defined there because both of those x values lead to zeros in the denominator, which cannot be evaluated, and so the function is not defined there. But near there, some pretty fun things start to happen. And when we hear the phrase near some particular x value, that might be a hint that some of the ideas that we've been discussing with limits might be interesting to consider, right? Limits talk about behavior near a point, not at a point, right? All these little tiny intervals near it. So let's start by looking at values near 2, right? So I've plugged in some x values near 2 in this table, and we can see the values of k of x in the right-hand column, right? So if you start at the top of this table at 1.5, then x equals 1.9, 1.999, 1.999. And then from the bottom, we're starting from above 2, 2.5, 2.1, 2.01, and so on. And what we see in the outputs is that far away from 2, so here I'm saying far away is about a half a unit. The values are fairly comparable, right? We're inputting 1.5, getting 1.6, inputting 2.5, outputting 1.14. But as we get close to 2, the values popping out of k get large by quite a significant margin, right? We haven't changed the input between 2.1 and 2.01. We haven't changed the input very much, right? It's gotten, what, 9/10 of a unit smaller, and yet the output has jumped from 32, a little better than 32, to a little better than 3,000, right? So we've jumped up quite significantly, more than 3,000. And then as we go from 2.01 to 2.001, it becomes even more stark. We jump up into the hundreds of thousands, right? And if I were to get closer to 2 by adding zeros, you can see these numbers are so big now that the computer needs to use scientific notation, and we just keep adding. You can see that we're adding 2 to that exponent each time, meaning we're getting, each 0 is getting us 100 times bigger, right? So we're getting 10 times smaller, but 100 times bigger. We can do the same thing from the other side, adding 9s. We see the same behavior. We're adding powers of 10, powers of 100 to the value of the function, right? So it explodes off to these huge values that we see in this graph, right? If I zoom out and you look, let's put the asymptote back up. As we approach this asymptote at 2, as we put in values of x closer and closer to 2, the function itself is outputting. You can see these dots are some of the values from the table, right? To get to the next value, I have to zoom incredibly far out, right? And I'll have to zoom incredibly far out to start seeing the next ones, right? So we're getting to a point where we've zoomed out so far that we can see almost nothing. This is getting hard to control. That we can see almost nothing of the function, right? We're so far away that the rest of the function kind of disappears from us. Let's just fix this. Let's move this. And let's fix this. Okay, so now we can see it again. So there's some interesting behavior going on there, and we're looking at a point where our function can't be evaluated. So we're gonna think about limits, right? Let's do one thing first. Let's think about this exploding property. It's a good, I think, exercise in thinking about how numbers and functions work. Why do we have this explosion there? Well, we've got two factors in the denominator of this function, the factor x plus 1 and the two factors of x minus 2. So near x equals 2, x plus 1 is approximately 3. And near x equals 2, x minus 2 is approximately 0. Okay. So why does 1, well, let me say more. So this factor that's approximately 3 turns out to not matter very much. Let's see why. Let's consider two numbers near 3 in the denominator. 1.31 and 3.1 and 3.01 in our denominator, right? Those are two numbers that are pretty close together. Let's see exactly how close. So let's just put in 1 divided by 3.1 and 1 divided by 3.01. Right, notice how close together these numbers are, right? They're both 0.3 and then one's 0.33 and one goes 0.32. And so they're about a 1/100th difference, right? They're very close together. They're not very different numbers. If we did 3.01 to the next power of 10 closer, right? These are even closer together, right? And they're always about 1/3, right? We know approximating 1/3 at 0.3 or 0.33. It's a pretty decent approximation. And so both of these are pretty similar numbers. All right, so I think it's reasonable to say that these are close. But something very different happens near x equals 2. If we have a factor of something near 0 in the denominator, like let's use the same change. Are these very similar, right? Look at how close these two numbers are, but these ones near 0 are not very similar, right? Let's just write this a little differently. This is 1/110, which is equal to 10. This one's 1/1/100th, which is equal to 100. So now the outputs are very different, right? Before they were very, very close, but near 0, these two outputs are very, very, very different. What's even worse is we're squaring this thing. So actually, this should be 1/10 squared, which makes it 100. So we'd have a 100 here. And this squared, we're going to end up with 10,000 there. So now the difference between when we shift these little factors, when we change the value of x very small, a very small amount, that 1 over x plus 1 factor doesn't change very much. But the 1 over x minus 2 changes significantly, right? So k of x near x equals 2 is approximately, that's a terrible approximately sign, is approximately 1/3 times this other factor, 1 over x minus 2 squared, right? This one doesn't change much. It's always about 1/3. This one does all the work. And as it gets closer and closer to 0, we get this explosion, which is exactly what we saw in the values here, right? That it's always, so what did we do? 0.01. That's about a 10,000. So that would be at 2.01. When you have 2 minus 2.01, you get negative 0.01, but we're squaring it, so the negative doesn't matter. You get 10,000 divided by 3. 10,000 divided by 3 would give you 3,333.3333. we're not quite 1/3 because this first factor isn't exactly 1/3 and we get something really close to that, right? And so as we keep getting closer to 0, that 1/3 doesn't do much, but that second factor explodes. A similar thing happens at x equals -1. I'm going to leave that analysis up to you to think about what's going on with the values there. But now let's bring this over to limits. So let's think about the limit as x goes to 2 of k of x. Our definition of limits is that we say a function has a limit as x goes to a value if we can make the function as close as we want to that value by taking x close enough to the number we're going towards, right? In this case, is there some number that k of x is getting closer and closer to by taking x as close as we want to 2? The obvious answer is no. There is no number we're getting closer to. It's just getting bigger and bigger and bigger. This limit does not exist, okay? I want to stress this a lot. This limit does not exist, but we are going to write something that makes us feel like it does exist. The limit as x goes to 2 of k of x is equal to infinity. We write this. What we mean is the limit does not exist, but we can make the function k of x arbitrarily large by taking x close to 2. Okay? So that's what we mean by this symbol, right? Some people might say this is an abusive notation. This limit doesn't exist, and yet we're writing it as if it does. But we're saying it's equal to a thing that's not a number, right? A limit gives us a number. This language, this collection of symbols means specifically this limit doesn't exist, but I still want to tell you something about the function, right? I want to tell you that this function does something very specific at 2. Lots of functions don't exist at values, and sometimes there's just a hole there. This isn't that. This gets as big as you want as we get closer and closer to that value. All right, let's look at our graph again. Now let's look at x equals -1. Notice we have different things happening depending on how we approach x equals -1. What we would say here is the limit as x goes to 1 from the positive side, right? This is our one-sided limits. So as we come from the right, values bigger than -1, we get a similar sort of thing happening that we saw before, right? Where we looked at x equals 2. We have one of the factors doesn't change much. The one that's getting closer and closer to 0 causes this thing to explode. The difference being here, the x minus 2 factor, because it's squared, is always positive. And if we're above, depending on whether we're above or below -1, the x plus 1 factor is going to be positive or negative. So that's going to determine the sign. But the part about getting close to 1 is going to cause us to shoot off to positive or negative infinity. So from the right, we're going to positive infinity. And from the left, we're going to negative infinity, right? Both of these mean what we have up here. The limit doesn't exist. But as I approach 1 from the positive side, from the right, I can make k of x as large as you want in the positive direction. And as I approach x from the left, as I approach it from below, from the negative side, I can make k of x as large as you want, but in the negative direction, by taking our x values close to -1. Okay, so even though the limits don't exist, we're still using this notation because it's such a closely aligned idea, getting closer and closer to something. to describe some very specific behavior. It's important to know when this happens, right? If this is a function mapping some chemical reaction, this might be where the thing explodes, and you want to know when that's going to happen, what values to not approach for whatever it might mean. I don't know any chemistry. So let's finish this with some definitions. Let's just go to a new page. All right. So we have several different kinds of limits. I think you can figure out from this, there's just all the different combinations we can have here. So if we have, if f of x is defined on AB, sorry, I want to just do it in the same order so I don't get lost. On BA, if, actually, let's write this as suppose. Suppose f of x is defined on AB. If the values of f increase without bound as x approaches A, with x less than A, so we're approaching from below, we write the limit as x goes to A from below of f of x is equal to negative infinity. If the values of f, so some people use the language decrease. I hate using that language. Even though going in the negative direction is decreasing, I think it's nicer in my head to say increase in the negative direction, because then I understand that it's still big numbers, just which direction they're pointing in, right? The negative isn't really about the size, it's about the direction. And it's negative a billion is still a huge negative number, not a decreasing number, even though it technically is. So I'm going to write it that way. If the values of f increase in the negative direction without bound as x goes to A, all right, so with x below A, we write the limit as x goes to A from the negative direction of f of x is equal. Oh, I wrote negative infinity up here for some reason. This one's just infinity. Now we're at negative infinity. Okay, so there's our first two kinds of limits. The next two are pretty similar. We'll say, suppose f of x is defined on AC if values of f increase without bound as x goes to A, with x greater than A, we write the limit as x goes to A from the positive side of f of x equals infinity, right? Similar switch here. If the values of f increase, let's say increase negatively, without bound, right? Without bound just means they keep getting smaller and smaller, or larger and larger and larger. As x goes to A, with x greater than A, we write the limit as x goes to A from the positive side of f of x is negative infinity. And then finally, suppose f of x is defined on an open interval containing A but not at A, if the limit as x goes to A from the negative side of f of x is equal to the limit as x goes to A from the positive side of f of x, and they're both equal to infinity, then we just say the limit as x goes to A of f of x is equal to infinity. If the limit as x goes to A from the negative side is equal to the limit as x goes to A from the positive side, and they're both equal to negative infinity as described above, then the limit as x goes to A of f of x is negative infinity. That's what we write, right? So we saw examples like this in this graph here, right? As we approach 2, both of them go to positive infinity, so we just say the limit of the function there is positive infinity, and we know that it means it doesn't matter which side we approach it from. On the other hand, as we approach -1, as we approach it from above, we're going to positive infinity. As we approach it from below, we're going to negative infinity, okay? These definitions are pretty wordy. What we really need to understand is I think it's easier to understand from these pictures, right? What's happening as we approach these undefined values. We shoot off in different directions, okay? We also use these to give us a definition of asymptotes, right? When most of us first encounter asymptotes, we're just told there are these places where they shoot off, but we can now use the terminology of limits, that where any of these things occur, where any of these kind of limits occur, we say the function has an asymptote, right? That's what it's telling us. Asymptotes tell us where our limits are going to positive or negative infinity. One typical place we'll always see this, if n is positive integer, if n is even, then the limit as x goes to A of 1 over x minus A to the n is going to be equal to infinity. If n is odd, then we'll have the limit as x goes to A from the positive side, 1 over x minus A to the n is infinity, and the limit as x goes to A from the negative side of 1 over x minus A to the n is negative infinity, right? So if we have a factor of, if we have a reciprocal of a little power binomial there, as we get close to A, we're getting things close to 0, and then we're putting a power on it. If that power is even, we're getting these tiny, tiny numbers. If we're approaching from one side, it's positive, from the other side, it's negative, but then we're squaring it, or 4th power, or 8th power, and it's always coming out an incredibly tiny positive number. And then we have 1 over an incredibly tiny positive number, we get an incredibly large positive number. When n is odd, it depends on which direction we're coming to it from, right? That if we're above the asymptote, the place where it's not defined, A, x minus A is going to be positive, and then it's an incredibly small positive number, and we take it to some power, and so we get an even smaller positive number, and then we take the reciprocal, we get an incredibly large positive number. But if we're below, it's negative, and we're taking it to an odd power, so a negative comes out. So we get incredibly tiny negative numbers, we take the reciprocal, we get incredibly large negative numbers, okay? So these are not the only places we'll see asymptotes. A couple other places we already know about. If we take the limit as x goes to 0, we could say the natural log function. I'm going to say any log function, so I'm just putting b there to be any base of a logarithm. We're going to get negative infinity, right? And you might remember the graph of log functions look like this. not defined at 0, and they get increasingly negative as we approach 0. We also have some trig functions. For example, let's just sketch, let's do, let's put in some asymptotes for tangent. So we have negative pi over 2, negative 3 pi over 2, positive pi over 2, 3 pi over 2. The graph of tangent, this is tangent of x, does this. It's got an infinite supply of asymptotes, right? So for example, the limit as x goes to pi over 2 of the tangent of x, it's pi, it goes to pi over 2 from below. So here's pi over 2, this first asymptote to the right of 0. As we approach it from values below this, our function shoots off to infinity. If we approach it from above, it's going down towards negative infinity, which is a nonsense statement. It's getting increasingly small or increasingly large in the negative direction. Right. And then of course we can do this for each of these asymptotes, and this goes on forever. Other trig functions, secant, cosecant, will have asymptotes as well. And there's other things out there that we can find that have them. But the big ones are what we've talked a little bit about so far. We'll encounter more as we go forward. Okay, that's it for this one. Thanks everybody. See you next time.